Most structural deviations are invisible at first glance. In this fictional project, we compare structural execution versus design and show how small deviations become expensive problems. Model versus reality tells the true story. Week 6. Structure is progressing well. Visually, everything looks correct. A 10-floor reinforced concrete building on a tight schedule with weekly structural pours. The schedule is aggressive, driving a demanding weekly cycle. The BIM is the definitive baseline, a digital twin for every structural element, from foundations to the final roof slab. The job site is the outcome of labor, materials, and real site conditions. The challenge is managing deviation effectively, not eliminating it entirely. By week 6, the concrete frames stand tall. Slabs appear flat and level to the naked eye.
A site manager walks the floor and says, "Looks fine."
That phrase often conceals significant unquantified risk. Visual checks are subjective. They do not replace data-driven verification. What looks fine can mask inconsistencies that disrupt later trades. Small differences between model and as-built are where problems start. A column slightly misplaced. A slab poured a few millimeters high or low. A beam marginally off its design axis. Because buildings are interconnected, these minor errors compound. One shifted column forces adjustments above. The ripple effect propagates through MEP systems and facade. Facade installation starts to feel these shifts. One full floor per week leaves little room for error. The model is the yardstick for quality control and verification. Resolve clashes digitally before costly rework happens on site. Each step must be accurate and on schedule so the next trades can proceed. The pace assumes each completed floor is an accurate base for the next. If one floor deviates from the model, it affects the next floor. Cumulative error grows up the structure. High speed and high stakes enable the "looks fine" trap. A quick visual check at day's end may seem sufficient. Between what is visually acceptable and geometrically correct, risks germinate. Relying on BIM as the baseline makes objective verification an operational necessity. In the early stages of the frame's erection, deviations are subtle, measured in single-digit millimeters. A third-floor survey might reveal several columns off their grid center lines by 5 to 8 millimeters. On its own, such a shift is usually within tolerance and not an immediate structural concern. Slab elevations may show localized areas 6 millimeters high and others 4 millimeters low. A primary beam could be 7 millimeters off its intended axis. Individually small, these are often dismissed as normal construction. A misaligned column can be accommodated, a minor slab variation corrected during fit-out. The danger is not any single error, but their cumulative and interactive effects. Construction is an interconnected system. Errors ripple outward and upward. If a row of columns pushes outward, edge beams follow. Next floor formwork references as built positions. A sub-centimeter deviation on one floor can become multi-centimeters by the roof, impacting facade and precast. Minor slab elevation variations create steps at construction joints, affecting long duct or pipe runs. The MEP contractor must reroute services or perform costly on-site modifications. These are the tangible costs of millimeters adding up. To manage quality, define tolerance clearly and mutually. Tolerance is the permissible range between design intent and constructed reality. Start with the design position, precise model or drawing geometry. The actual position is what is measured after construction. The difference is the deviation. A tolerance band defines when deviation becomes a non-conformance. These limits are based on structural needs, downstream trades, and industry standards. Example: verticality must not deviate more than 1/1000, with plus 12 mm from design centerline per floor. A fifth floor scan captures all new columns. Data shows column C4 leaning, centerline at the top 15 mm east of design. 15 exceeds 12. C4 is out of tolerance. This triggers structured review, not blame. Document, notify, and assess. Does it pose structural risk? Affect beam connections next floor? Can facade still install? Quantified data enables accepting the deviation or requiring remedial action before the next pour. Looks fine is not a measurement. It creates hidden technical debt. The eye misses small geometric deviations over distance. Column leaning 15 millimeters, virtually imperceptible. A 20 millimeter slab dip, also imperceptible. Finishes can hide misalignment. They do not fix geometry. Tight MEP routes fail if a beam is built 100 millimeters low. A coordinated model becomes a real-world clash. Rerouting triggers further clashes, delays, and costs. Reality capture lets teams move beyond visual checks to quantify as-built conditions. It frequently reveals 3 accumulating structural deviations. First, column verticality. A slight lean within one floor can drift significantly over many floors. 5 millimeters per floor becomes 50 at the roof, affecting elevator rails and facade alignment. Second, slab elevation. One bay 10 millimeters high, the next 8 low, an 18 millimeter step emerges, challenging finishes and gravity systems. Third, floor plate shift or rotation, e.g., 15 millimeters north and 0.1 degree. Vertical shafts begin to stair-step and services struggle. Heat maps make extent and location immediately apparent. Millions of points distilled into an actionable report before issues become irreversible. Responsible verification starts with correct alignment to the project control network, then to the BIM. Software computes distances from every scan point to the design surfaces. Analysis is governed by agreed tolerance thresholds. Red marks high outside areas. Blue marks low inside. Green indicates intolerance zones. Reports include precise, objective measurements at critical points. Use neutral language, measured deviation plus 18 mm to focus on problem solving, not blame. Data replaces contentious visual debates with objective evidence. The conversation centers on technical implications and solutions. Data becomes the impartial arbiter for faster, collaborative decisions. Decide, accept as is, adjust design and reissue drawings, or remediate, such as grinding a high slab or modifying formwork. Good reporting is not about blaming, it is about clarity. Include quantified deviations, visual evidence, neutral language, and actionable recommendations. A clear page links measurement to impact and next steps. In structural execution, small deviations are inevitable. Ignoring them is optional. Do you define structural tolerances on your projects? How do you verify execution accuracy? Have you discovered deviations too late? Comment your experience with structural deviations and check the link